Now, why did Landau Lifshitz? Yeah, it turns out such a term only arises if the bulk dual has a Chern-Simons term in addition to the Maxwell gauge field, but this Chern-Simons term exists in the bulk dual to n equals 4 Yang-Mills. Okay, now Landau Lifshitz ignored such a term, and I don't really know why. But perhaps one reason that they did was, because they use this argument a lot in that chapter, is that they thought that such a term would be inconsistent with having a positive divergence entropy current. However, we get this out of gravity. This area increase theorem ensures that we get a positive divergence entropy current. So we went through the same thing again. We, meaning my students, wrote the paper in which this term appeared, and then we got an email from various people, including Sohn, saying such a term is impossible because it violates positivity of the divergence entropy current. And then we worked out the map to the event horizons, and it's not. It doesn't. This thing is positive divergence. However, in this case, there was something here. You see, in a beautiful paper by Sohn and Soroka, what they realized was that there is a constraint coming from positivity of the entropy current. Only that constraint doesn't set this term to 0, but determines the coefficient of this term in terms of the coefficient of the U1 cube anomaly of this global current. And this argument gives you a result that's consistent with what you find from ADS-CFT, but is liberated from it now because it's a general field theory argument made on general consistency grounds. So it applies to every theory which has a global symmetry that you're interested in that has a U1 cube anomaly. Such a term not only can appear in its fluid dynamical description, but must appear with a coefficient that you can predict on general grounds. And for this reason may have experimental consequences. Just as a 1-minute aside, I think this is a good example of the kind of impact string theory can have an experiment. In that, you do some general calculation. You're working with a theoretically consistent system. So you do some general calculations in a theory that's not very interesting to experimentalists, but you discover some general principles, then you learn to generalize beyond your theory. And those general principles can apply to experiment. Okay, so it's a very weak way, but at least it's one way. Okay. Fine. It's recently been realized in the last 2 or 3 years that there exist asymptotically ADS charged black-brane solutions in the presence of condensates of charged scalar fields. This realization was made by Gupsa, at least in our community. And it's possible to replay the story described above. Some work has been done here, more is under progress, to obtain the gravitational dual description of superfluid dynamics. This is sort of interesting because superfluidity has more interesting dynamics than ordinary fluid dynamics. And sort of interesting, and there may be a window of opportunity here, to discover things that the superfluidity people hadn't realized, maybe. Okay, so far we studied the gravity dual of locally equilibrated fluids in fluid dynamics. Now, fluid dynamics can be thought of as the physical process in which something that's locally equilibrated slowly dynamically evolves towards global equilibrium. From the point of view of somebody who's interested in the process of equilibration, it's a very tame process. It's a process in which most of the interesting stuff has already happened. Okay, now you can ask, so you've got this great gravity description, surely you can use it to do more than study this relatively tame process. Can't you use it to study the formation of equilibrium? Start with something that is not at all equilibrated, something like a pure state, and try to understand how it evolves towards thermal equilibrium. Of course you can in principle, but it's just a problem of solving a nonlinear differential equation, but it is a problem of solving a nonlinear differential equation. And in practice it's often very hard to say much about this. However, in certain examples, sort of tame examples, you can control, okay, I should say firstly qualitatively. Qualitatively, what is the process of equilibration and field theory mapped to gravity? You see, there's an inevitability about equilibration in field theory. You put some energy into a system, let it stand, it equilibrates, no matter what the details are. You can ask, is there an inevitable process like this in gravity? And in ADS space, which is like a box, there is, with enough energy density, you put enough energy density into it, it will inevitably form a black hole. Okay? So these two inevitabilities map to each other. And the process of equilibration, local equilibration, is the process of black hole formation. So, you know, this is another thing, that two interesting processes in sort of interesting to different communities, which can map to each other. They're both hard processes, and the challenge is to find, you know, an interesting and universal enough question for the statistical mechanist that you can answer, that is effectively answerable using gravity. There are various, you know, interesting phenomena in this game. For instance, the phenomenon of chop-twig scaling, which may well map to something interesting in the process of equilibration. But while there's some work been done there, including by myself, I think that the best question here has not yet been asked. Okay, so finally we come to the conclusions. Just to conclude this talk. So asymptotically ADS d+1 gravity reduces in the long wavelength limit to the equations of d+1 dimensional Navier-Stokes equations with gravitationally determined dissipative parameters. Okay, the gravitationally determined fluid dynamical system has no free parameters and so enjoys, in some sense, a degree of universality. Values of all dissipative constants in this fluid dynamical system are interesting and sometimes surprising, as in the case of charged fluid dynamics. Okay, this map now allows us, in principle, to reword any interesting open question in fluid dynamics into an interesting open question. Well, into a question about gravity. Of course, mapping two unsolvable problems to each other is not much progress. However, you might hope that, you know, the kind of interesting problem in fluid dynamics that could win you $1 million from the Clay Foundation somehow has a more tractable structure when seen in terms of gravity, and that hope might be based on the extra dimension of gravity, which may allow you to separate scales in a fluid dynamical problem in which all scales are put together at once somehow. This is a fantasy, but it's perhaps not a completely unrealistic fantasy. It would be really fun if you could use gravity to, you know, to say something about turbulence. I should say that though there have been many papers, in my opinion, there hasn't been much progress yet on this issue, and maybe there never will, but who knows. Okay. And then finally, I think it would be very interesting to extend this connection past the large N of classical limit. Interesting in many ways. Interesting in many ways. But, okay, that's it. Thank you.